So let's take a look. We're going to talk about water and solubility. So we're going to talk a little bit more about water and its ability to dissolve things later. But first we'll address kind of a special notation with it. When we go through and look at water, it's composed of the oxygen, and then we have two hydrogens. And it's in that bent shape. Okay, it's in that bent shape going back to Lewis structure all the way back in Unit 1, and we could go back and evaluate that. Okay? When I now come in as a secondary observer, if I came in and looked at the water molecule from this side, what would I see? I would see electrons. What charge are those electrons? Negative. Okay, so from that side, I'm seeing a negative. If I come in and look at the water molecule from this side, what do I see? I see hydrogen. Right? There's no lone pairs there, so I don't necessarily see electrons. But doesn't hydrogen have an electron?
In that case, it has two.
Okay. Hydrogen comes in with one electron, and in this case, you're saying it has two. It has access to do. Where are those? Where's that access?
That line right there.
The line representing the bond. Right? Well, if those electrons are in that line, if I come in from this bottom arrow, am I seeing those electrons? No. What am I seeing instead? What part of the hydrogen am I seeing? I'm seeing the nucleus. What charge is the nucleus? Positive. So when I look at this structure from this angle, I end up seeing a positive. So water, depending on which way you look at the molecule, we will see either a positive or a negative aspect to it. Okay? Those are not formal positives and negatives. Those are partial positives and negatives. Okay? So it's a changing in the electron density. Okay? We've seen a symbol for change before, the change for temperature. Okay? For instance, was what symbol? You remember that?
Triangle.
A triangle. Okay? Which, if we're going to get extra specific, is not a triangle, it's a delta. Okay? It's the capital Greek letter delta. So I could go through and say, well, this is a change in charge, a change being positive. The problem with that is delta is typically referred to for temperature, or adding heat. So I don't want to use a capital delta. But I still want the intent behind the delta, that delta being changed. So if I can't use a capital delta, I'll use a lowercase delta. Okay? Which I may be a little bit sloppy on, but that's a lowercase delta. That lowercase delta is representing a partial charge. When we look at the molecule from the top and we see the oxygen, we see a partial charge of a negative. When we look towards the hydrogen, we see a partial charge of a positive. Right? Autumn, there's a question.
Is it supposed to look like an S, an infinity, or a hook?
So there's a little bit of a hook, and then it loops back on itself. Okay? So if we think about, that's a D, isn't it? Yeah, there it is. That looks really weird. Nope, that is a D. Okay? The delta symbol is effectively a D, except you just did a hook and you've looped up a little bit higher. Okay, so it is still that lowercase d shape. Well, when you look at a capital D, right, isn't that really like capital D? Doesn't that kind of look like a triangle that just kind of fell over?
That's like an isosceles triangle, but it's kind of equilateral. Or is that an acute? I'm not sure. No, wait, that is an acute triangle.
As opposed to an ugly one? Sorry. Greg's not here. We got to do something. Okay? Yeah. So, what happens with the water molecule now? Those charges, are those charges stable? No, charge is inherently an unstable thing. So water molecules will now orient themselves in space to try and neutralize that charge. That means the negative of one part is going to associate with the positive of another. So if we look right in at the middle part, right through here, you'll notice that we're taking the partial positive of one hydrogen and associating it with the partial negative of that oxygen. All right? So those are now interacting strongly, so strongly that they're actually showing some kind of connectivity there. You'll notice they're not showing a solid line. Why not? What is a solid line? A chemical bond. Is it a chemical bond? No. Okay? But it is a strong attraction there. Because it is a strong enough attraction, we're trying to call attention to that attraction, and so they're showing those little dots in between to represent that. Okay? That attraction is so strong that we want to associate a name with it. Okay? And we'll rant and rave about this a little bit later as well. What name should we associate to it? Well, it's involving hydrogen, so we'll call it hydrogen. And it's some kind of attraction between them. Well, what is the attraction between atoms called? A bond. So we'll call it a hydrogen bond. Is it a bond? No. Why are we calling it a hydrogen bond? Because the moron that came up with the name decided to confuse the rest of the world by calling it a hydrogen bond. It is not a chemical bond. Never reference it as a chemical bond. If a biologist tells you it's a chemical bond, they are wrong. It is not a chemical bond. Okay? What's that?
Tell them it's wrong too.
And you can tell them it's wrong. And if they're like, no, no, it totally is, you can tell them, here's my chemistry instructor that told you are wrong. You can go take it up with him. Okay? And I will fight them tooth and nail on it. They're wrong. It is not a chemical bond. Okay? It is a very strong, attractive force that is not a chemical bond. Okay? When we look at the ability for water to dissolve certain compounds, say like salt. Salt is composed of what two things? Table salt.
Sodium, chloride.
Okay, we have sodium, and typically it's chloride. Sometimes you'll see iodine in there. Iodine is usually added as a supplement. Okay, those are now charges, right? So let's take a look at the chloride ion. In the ionic compound, we have sodiums around it to stabilize it. In water, what happens? It breaks apart. Why does the salt break apart, though?
Because chloride is negative.
Chloride is negative and sodium is positive, which means they stay together. You're saying it's all the same substance. Why would sodium and chloride break apart?
Because the oxygen is trying to neutralize its charge.
The oxygen in water tries to neutralize the negative charge of the oxygen by hooking up with sodium. What would hook up with the chloride? Hydrogen. Okay. Which interaction is stronger? What is the connection between sodium and chloride called? It is called a chemical bond. It's called an ionic bond. What is the connection between the hydrogen and the chloride? Is that a chemical bond? That would be potentially hydrogen bonding. It is not a chemical bond. Which one's stronger? Chemical bond. So why would sodium chloride break up if it's now forming a weaker interaction?
Something to do with solubility.
When we look at water, what happens? Is it just a single water molecule that's interacting with it? It's a bunch of different water molecules. Because we get more of that weaker interaction, that larger amount of the weaker interaction ends up generating a more neutral or stable structure than it was in the original salt. That's why the salt breaks apart. Okay? So when we think about the interactions of substances, it's not just the brute strength, but it's also the amount. Okay? The nice analogy that we could look with, how many of you would pick a fight with a 5-year-old kid or the mountain? You all know who the mountain is, right? Yeah. Game of Thrones, yeah. Who are you going to pick a fight with? The mountain or a 5-year-old kid?
What's it over?
The mountain.
Doesn't matter.
The mountain. What
I mean, if I'm motivated enough.
I don't know if he has a passport.
If it's over Dolores, I'll fight that guy.
I'll gladly die by his hand.
Okay,
I'll give him the tape of his life.
okay, for a piece of candy, you just got to get a piece of candy. You have no weapons, hand to
That
hand.
guy eats candy, so obviously I wouldn't have right there. That means
Maybe like
no
take
carbs,
Or-
no sugars,
What would happen if we went through and picked, say, the mountain versus 5 million 5-year-old kids?
He would still
You'll-
decimate them.
It's not them, it's you. It's you. Okay? You're probably not going to beat the 5 million kids, but you might be able to beat the mountain. Okay? He's big and huge. You could just run around real fast and tire him out. Okay? So the amount also contributes. It's not just the strength of things. Okay? So the next part is we're now going to look at the ability for something to dissolve. Okay? This is now talking about solubility. There are 3 different ways that we can reference a solution: as unsaturated, saturated, or supersaturated. Okay, so if I pick, come on, pen, this point, that little red point, what can you tell me about that red point?
Temperature is 20 degrees Celsius.
It is 20 degrees Celsius. That looks like minus 20 degrees. So it is 20 degrees Celsius. What else can you tell me?
And there are 200 grams of solute dissolved in 100 milliliters.
200 grams of solute. Can somebody do better? And you said 100 milliliters of water. So
30 grams of sugar solute.
how do you know it's sugar?
It says on the graph.
It says on the graph. So it's using the information within the graph. Okay? So at that point, at 20 degrees Celsius, I get 200 grams of sugar. Okay? There's another thing that you can tell me about that point.
It would be pretty bad Kool-Aid.
Bad Kool-Aid, as in like good Kool-Aid? Or?
Nah, as in bad Kool-Aid. But the more you went up, the Kool-Aid would get better.
We could argue that, but there's another
Agree.
point
I
here.
know where you're going. I completely agree.
Can I dissolve any more sugar
Yeah.
at 20 degrees Celsius? No. This point shows the saturation limit. That point is saturated. I can't dissolve any more sugar at that temperature. If I increase the temperature, I could dissolve more sugar. How much more sugar could I dissolve? Let's increase it to 80 degrees Celsius, because we're hearing somebody saying that, well, this is now going to be a better Kool-Aid. 80 degrees Celsius is roughly kind of a mildly, that's not really mild, that's pretty much a cup of coffee. Your Kool-Aid is now going to burn your mouth. So we got to think about the temperature a little bit there. Okay? So, but we're taking the same solution. So it's just 80 degrees Celsius. Okay, what can you tell me about that blue point now? What can you tell me?
That's undersaturated.
Okay. It's 80 degrees Celsius. How much sugar is dissolved in it?
200 grams.
200 grams. Could I dissolve more sugar? How much more sugar could I dissolve? Whatever that distance is. That was supposed to be one of those parenthetical things. Right? I could get another 150 grams dissolved. That means at this blue point, what am I?
Undersaturated.
Unsaturated or undersaturated. Okay, I could dissolve more. Okay, so let's heat it up to that 80 degrees. We get it up to that point, and now I decide, because we've been adjusting temperatures, now I decide I'm going to cool it down. What happens? So we heated it up, then we added more sugar, and now I want to cool it down. I'm going to cool it back down to 20 degrees Celsius. What happens when I cool it down? Right? If I am incredibly lucky in how this system worked out, what happens? All of that, we'll address that in a second. Okay? In that cooling process, I now have all of that sugar still dissolved. I'm above my saturation limit though, which means I am now supersaturated. Okay? Can we generate supersaturated solutions? Absolutely. Have you ever seen the like rock candy? You dissolve all the sugar in boiling water and you stick the little rod or the string, whatever, into it, and then it crystallizes around it. That's because you formed a supersaturated solution. It wants to crystallize out. Remember that sodium acetate where we watched that idiot burn his hand? What did he generate? He made a supersaturated solution. Right? As long as we leave the solution alone, we can trick the solution into thinking it's okay to be dissolved. The instant we touch it or impact it, that now convinces the solution, oh crap, I'm well beyond the saturation limit. We shouldn't be here. So what happens as we move that direction? Okay, we get solid reforming. Okay, that is now a saturation curve and how we move through it. The line is our saturation limit. If we're under that line, that means we're undersaturated. If we're above it, we're supersaturated. Yes?
So if you're like cooking and you're making like a glaze, and you put a bunch of sugar in it, and then you have to cool it back down, it just thickens, but it doesn't like separate.
So it depends when you cook how much you're heating it and other kind of factors that go with it. Sometimes you've got enough liquid in there that it maintains kind of a solution. You could be melting the sugar a little bit more as opposed to causing it to crystallize. Not all curves show the same thing. So what we've got here is now a super complicated version. It's the same thing as the sugar and salt one, except a lot more substances. What do you notice as a general trend? What's that?
They go up.
They go up as the temperature goes up. Does that make sense?
No.
As I increase temperature, more solid dissolves. Why does that make sense? What happens to a solid when I increase the temperature? It becomes a liquid. What is a solution? A liquid. So as I increase temperature, I'm doing two things. The increase of the temperature causes the solid to transition to becoming more mobile, like a liquid. Okay? And when I make a solution, the solid has now become more mobile because it's now in solution. Both dissolving things and temperature contribute to the same general trend for solids. Okay? You'll notice that that trend isn't perfect. Some things don't follow the trend, like our cerium sulfate. We could go back and evaluate those kind of things. That's not the scope of this class, so we aren't going to worry about it. It's looking more at the general trends and making sense of it. Does that work? Okay. So, here's a chemical reaction. What kind of chemical reaction is this? It is a double replacement. So we're recognizing patterns within it. Is this double replacement balanced? Cool, at least an attempt was made to balance it. I think it is actually balanced. Okay, so we could start to do conversions between one substance to another using this chemical equation. Okay, so let's add a little fun thing on this. Silver bromide cures cancer. So I want to make silver bromide. Why would I want to make something that cures cancer? I could make lots of money. Okay, so we've got that. Or we're really nice and we're trying to save people. Okay, so we could make lots of money. So I want to be able to figure out how much silver bromide I could make so that I can tie that to how much money. Because maybe it turns out that in this chemical reaction I can't make that much. Okay? So what would I mix to make the silver bromide? We have a chemical equation. How would I make the silver bromide? I would take aluminum bromide and silver nitrate and I would mix those. Okay, how do I measure the aluminum bromide? Okay, so I go into the lab and I pour out my aluminum bromide on my mole measuring device and it tells me the moles. It tells me grams. Am I actually going to be measuring grams for aluminum bromide?
You probably be doing like
Probably doing kilograms.
Okay, kilograms. It's an interesting theory. When I measured out, let's say 5 grams of the aluminum bromide, is that 5 grams of aluminum bromide? No, why not? Nope.
Moisture in the air.
They're one thing. If I measure out that 5 grams, did I actually measure out 5 grams of aluminum bromide?
It's aqueous.
What does aqueous mean?
Weigh it in liters.
What does aqueous mean?
It's only water.
Dissolved in water. So when I measured out that 5 grams, what is that 5 grams? That is the mass of
Solid.
silver bromide and water. Is water in my chemical equation? No. So if I measure out the mass of aluminum bromide, is that going to help me out? Nope, because I've got it in solution. So that doesn't work. Okay? The other thing, it's a liquid. Should I be measuring the mass of a liquid? No, what should I be measuring the liquid? The volume. So now I switch, okay, I switch to volume. Now what am I measuring the volume of? Not the unit. What am I measuring the volume of? What is the substance? An aqueous solution. So is that volume aluminum bromide? No, it's a mixture of aluminum bromide and water. Again, is the water in the chemical equation? No. So if I've got this solution, I can't predict how much silver bromide comes out of this because now I don't have a unit that allows me to separate the water from the aluminum bromide. I would need to know the concentration of the aluminum bromide in the solution. How much is there? Okay. This is kind of an important thing to at least consider and think about. Okay. Why? I know the class may be young, but we can at least consider potential theoretical situations where we're looking at concentrations of certain solutions, say that are measured by ABV. ABV. Alcohol by volume. Are certain solutions of alcohol by volume going to be important for us to know what that ABV is? Yes. Why? Is something that has an ABV of 4 going to have the same interaction as an ABV of 99? No. We're going to get massively different responses, okay, with equal volumes. Okay. What is ABV? It is the amount of alcohol in the solution by volume. Okay. It's a concentration. Okay. We don't need to really know specifics of that because we aren't ultimately doing a conversion with our alcohol by volume. In chemistry, what are we attempting to do? A conversion, which means we need a concentration that allows us to convert swiftly and easily. What units would we need to, should we choose for our concentration?
Liters.
Right, liters. Liters of what?
Aluminum bromide, aqueous. Liters of solution.
Liters of our solution. All right, what else would we need to know? Too far. Step back from the ledge. What else do I need to know about my solution? If I'm going to make the silver bromide, I'm trying to... Concentration of what? What am I looking at a concentration? Just the solution?
Concentration of the...
Whatever the thing is that's dissolved in the solution, right? I need to know what that thing is. That thing we'll call the solute. Okay, it's the thing that was dissolved in our solution. What is the measurement unit for the solute? Okay, grams. Have we seen a relationship between mass and volume before?
Yes.
Yes, that relationship was known as density. Is this going to be a confusing conversion factor then? Probably. Okay, why? This is relating two different substances, solute and solution, using mass and volume. Density is mass and volume for one substance. That gets dangerous. Okay? I could easily confuse this conversion factor with density. There's another reason why grams of solute is probably not useful. Remember, in chemistry, what am I trying to do? Trying to take two things, mix them together to do what? Make something else. What's the thing that describes how I convert one substance to another?
Reaction.
A chemical reaction. And what units are my chemical reaction in?
AMUs.
No. AMUs is a mass. Mass units do not show up in chemical reactions. Moles would work. Molecules would work. Any kind of counting unit would work. Is grams a counting unit? No. It's a mass measurement. Okay? So grams doesn't work. So what would be a better option instead of grams? moles. Why would moles be awesome? Now I don't have to do a gram to mole conversion using the periodic table. I'm already in my mole converter that would allow me to convert the substance through the chemical equation. I can shortcut one of my steps. That's pretty cool. Right? This also cannot be confused with density. Right? Because density is a mass per volume. This is now an amount of a substance in a total solution. So it's an entirely different converter. That's nice. I've got a separate thought process for this. Right? So the relationship or the units I choose are moles per liter. I will choose 1 as my liter, as my definition for this. What will the mole amount be? It's a nasty trick question. Kind of.
We may know.
No, it doesn't. And we'll address that hopefully today too. What number is going to show up in there for moles? Which Kool-Aid do you want to drink? 0.001 moles of sugar to 1 liter solution, or 5 moles of sugar?
It's a lot of sugar.
Says the guy that was like, let's make this supersaturated. Way to just backtrack on your theory. Okay? Can we dissolve differing amounts of a substance in a given volume? Yes, which means this answer for our moles will be given to you. Okay? That is somehow given to you. That is the concentration for that solution. Okay? When we try and determine the ABV, we don't sit there and drink, equal volumes of it and be like, I think that one was about 4%. Poof, never mind, that was 100. Okay? We want to know that measurement before we do the interaction. Okay? So that is something that would be calculated depending on how much stuff we decided to dissolve. Okay? So that is a kind of calculated or given concentration. Because this relationship is now going to be so common for our solutions in chemistry, we invent a new name for it. Just like we did for the mass to volume relationship. Right? Mass to volume is what? Density. You spat that out way too fast, which means we need a new name for the moles to volume relationship. We will call this molarity. Not to be confused with molar mass, molar weight, molecular mass, or molecule, or malaria. Okay? We have the molarity. Okay? Sometimes also referred to as molar. Okay? The instant you see molarity, you should immediately be writing moles per liter. Why? Moles per liter are actual measurements that we can control. Molarity is not a measurement. Okay? Just like when we talk about density, we write grams per milliliter. We don't write one density. Okay? So, there's our molarity. It's the moles of a substance per liters of the solution. What is the molarity of a solution containing 24.0 grams of sodium hydroxide in 0.1 liters of solution? Okay, so we're going to set this up a couple different ways. Number one, I'm solving for moles over liters. So, as my reporting, what information am I given? 24 grams of sodium hydroxide and 0.1 liters of solution. Is either of those things exactly what I want for an answer? One of them is. Which one? 0.1 liters is exactly what I want. I want liters. Okay, where do I want the liters to show up? In the bottom. So I'm going to write 0.100 liters on the bottom. Okay. Within that reporting of 0.100 liters, is there anything else in that box? Solution. So we could write solution. I'm okay. Is there anything else? That's it. Which means what's on top? Is 24.0 grams in the box with 0.100 liters? No. Okay, so what goes in the numerator? 1. Okay. The next step, okay, I've got 24.0 grams of sodium hydroxide. Where should I place that? The substance is sodium hydroxide. When I solve this all the way out, I want moles of sodium hydroxide located in the numerator, which means my 24.0 grams of sodium hydroxide should show up where? In the numerator. What should show up in the denominator? 1. Again, the given information. Some people will look at that and say, well, isn't that the same thing as writing 24.0 grams sodium, that's the sodium hydroxide, over 0.100 liters of solution? Numerically, yes. Mathematically, borderline. Based on the content given, no. What you've gone through and done is used a chemical or a equation to say that I want to divide those things. I want the substance over the volume. It's true, I do want the substance over the volume, but that, as it's written, says that that was a given conversion. That's not a given conversion. It was two separate pieces of information. Okay? Not a big deal. It's fine either way. I just wanted to at least point that out because at least one person did that. Right? Is grams of sodium hydroxide what you want for an answer? No, so what can you do? We need to get rid of the grams of sodium hydroxide and we want moles of sodium hydroxide. Where do I get that from? Periodic table, 1 mole, I'm trusting people, 40 grams.
Yep.
Sodium hydroxide. I can now punch it into the calculator and get an answer. Okay. The other way to do this. Molarity. What is molarity? It's moles over liters. Am I given the liters? Am I given the liters? Yes. 0.100 liters. Am I given the moles? No, so what do I need to do? I need to find moles. Moles of what? Moles of sodium hydroxide. What am I given about the sodium hydroxide? 24.0 grams of sodium hydroxide. How do I convert grams of sodium hydroxide into moles of sodium hydroxide? Periodic table. Okay, so 24 divided by 40 gets me my moles. What can I then do with that mole value? I can place that into that equation and I now solve. Both of those methods do the exact same thing. Both of those methods show all the unit work to support it. So both of those methods are valid and acceptable processes. Make sense? Okay. To kind of match the blue one, or that blue conversion, because the purple part of it, I think, is its own special thing. So if we look at the blue one, we could go through and say that 1 mole of sodium hydroxide equals 40 grams of sodium hydroxide. For your solve, what do you have? Well, we're given 24.0 grams of sodium hydroxide. How do I go from 40 to 24? So 40 times x equals 24. I need to multiply by 24 over 40, right? So what would I do the other side? Multiply by 24 over 40, and that would get me my moles of sodium hydroxide. Take a look at the blue salt down below. What did you do? 24 over 40. Okay? Both of those methods work. Both of those, again, must show the units. Don't just start writing numbers down. Okay? It will be unacceptable to tell me 1 equals 40. Okay? Because 1 does not equal 40. That is not valid. You can't say that as a true statement. Okay? I might know where you're trying to get to. You're trying to say, well, then x24, how do we do those? Okay? And now how would we get there? Until the units are there, that's not a valid statement. Make sense? Okay. Last one I want to throw out there. Okay. One option again with the bottom one, we went through and solved for the moles of sodium hydroxide. Okay, well I know I need to divide by the liters, so divide by 0.110 liters. Okay. Mathematically, if you enter that into the calculator, is that what you're going to get? Would that be right? 24 times 40 equals a number divided by 0.1. That would be your answer, right? Okay. Effectively, what you just wrote was 3 plus 1 equals, come on now, 4 divided by 2 equals 2. So 3 plus 1 equals 2. That order of operations makes that calculation invalid for that same reason. Just writing the divide by 0.1000 liters is also an invalid mathematical operation. Make sense? Okay. As far as point loss for show your work, minimal for my point of view, because I understand what you're trying to do. Okay. For future classes, they may not accept it. Okay. For instance, if you walked into a math class and said 3 plus 1 equals 2, you are going to be marked wrong, and you will not receive points. Right? Okay, so you should make sure that your work very clearly shows that you aren't stringing together equalities. Greg talked about this, I think, last week. Okay, what's that? It's like a run-on sentence. Right. So, how many grams of potassium dichromate are in 125.0 milliliters of a 0.150 capital M solute? What is capital M?
Molarity.
Capital M is molarity. What should molarity immediately be written as? 1.50 moles over liters. I saw a couple people doing this. 0.150 moles / liters. Knock it off. Okay? The problem with writing that / liters is that you don't recognize that liters is in the denominator. And you'll end up screwing up your conversion factors. Okay? Do not write the /. Okay? Well, I didn't make a mistake yet. Yet being a massive operative word. Do not write that /. Why is that / in existence? As a hat tip to Greg, writing technologies, typewriters, computers, that's the only reason we yet use a /. Otherwise, we'd show the full division in fraction. Okay? So we set this up for you guys to do the easy one. Now I'll do the harder one. What are we solving for? Grams of potassium dichromate. Okay? I've got a lot of information I could start with. I could start with the 125 milliliters, or I could start with the 0.150 moles. What do you guys think? Why do you want to start with the moles? Okay, so there's a propagation of the measurement unit. I would argue that we can ignore the measurement unit and look at the substance. The substance is in the numerator. Substance is in the numerator. Okay, so we could go ahead and start this calculation off with 0.150 moles of our potassium dichromate in 1 liter of solution. Do I want liters of solution? No, so what can I do? Get rid of liters of solution. Am I given liters of solution? I'm given milliliters, so I'm not given liters of solution. I need to do a conversion. The conversion factor I choose is to go to milliliters. Why milliliters? Because I know I've got milliliters given to me, so I can do milliliters of solution. That conversion factor, milli, means 10 to the minus 3. 10 to the power of 3, or 10 to the negative power of 3 goes with the core unit. The core unit is liters. Now times by my volume, which in this case was 125.0 milliliters of solution. The milliliters of solution cancel, the liters of solution cancel, and I would now have moles of potassium dichromate, and I would not be done because my answer is grams of potassium dichromate. So I have to initiate a new conversion factor. In that conversion factor, what do I want to have happen? The moles of potassium dichromate must cancel, and I need grams of potassium dichromate. Where do I find information about mass being related to moles? The periodic table. So I would look at the periodic table for potassium 39. How many potassiums do I have? 2 plus chromium, 52 times 2 plus, did I do that right? Yeah. Plus oxygen, 16 times 7. I'll do some math on the calculator, which gives me a number. 294.2 grams is 1 mole. My moles cancel, and I would now have grams of potassium dichromate. It's now just a question of entering it into the calculator, and I'm done. Make sense? What's the question, Ethan? So, and remember, some of this comes from what do you see, what do you feel comfortable with, okay? A lot of people will start with the number that's all by itself and just drop that in at the very front. The order doesn't matter. It's what you see and what allows you to move through it. Make sure that you have a logic behind each of those steps, and you're good to run. Make sense-ish? Hi. So, this next slide is a bit of a beast. Okay? It was going to be a super kind of evil thing, so we won't worry about it being super kind of evil. Okay? We've got a problem stated here. What I want you to do over the weekend is think about that problem and try and come up with the steps that you would have to do to solve the problem. Okay? If this means you have to solve the problem, that's okay. Go through and solve it. But again, it's the steps that become important. What are the steps that you have to identify as you move through it?
So do you want us to write it out with words?
I want you to attempt to write it out with words. This is not a only alphabetic characters thing. This can be like, this is where I would find these pieces. Not a bad idea to try and just do the full solve.
Yeah, it would. So that would be okay.
So if you do the full solve, then ask yourself, do the full solve, and then go back and look at your work at a later time and be, why did I start with this? Why did I pick this number to start off my writing? Why did I pick this formula to start off with my writing? How did I know this formula was the answer? Okay? Think about all of those pieces. There's something like 20-odd different pieces that go into this solve. A weakness in any one of those pieces causes the entire problem to fall apart. Right? That is why it is a challenging question and why it is not typically tested in first semester or fundamental chemistry. Second semester general chemistry, you could expect to see 2 of 3 of these per exam. Okay? So get some practice with it if you have to move forward. If you don't have to move forward, don't stress about it. There's a bunch of hidden text here. Don't worry about that text. Okay? Dimensional analysis. These are just summary slides. What are we starting with? What are we ending with? What are we starting with? How do we build conversion factors to move through? Okay? Some conversions. Think about all the conversions you've got. Where did they come from? Why do you know that conversion factor to be true? Okay, is it true? Okay, verify them. Start coming up with these lists of conversion factors to then come up with and decide, is that something I was supposed to memorize? Okay? Or is that something I can find somewhere else? Okay? Every time we've done these, we've been looking for different conversion factors. Think about where they're coming from so that you can think about why you would use them. Okay? Units, measurement, and a substance. Measurement and a substance. Okay? Those are important. You have to acknowledge those. Okay? In our second exam, most of that information was found on the exam. This third exam, most of that information is found in a chemical equation, which you may have to generate. It is found in the periodic table, which you have to interpret. that information is no longer explicitly stated. You have to find it. Once you have found it, then you have to follow a process. If your process is crap, it doesn't matter if you can find the conversion factors because you can't solve. Right? If you don't know where to find the conversion factors, but you have an awesome process, it also fails. Right? You have to be good at both. That is why we talked so much about process in the first or the second unit, so that we wouldn't be talking about process now, so that we could be focusing on where to find those conversion factors. Okay? So we need to be looking at both those pieces. As we continue through, what happens? Well, we brought in conversion factors for grams to moles, periodic table. We've brought in conversion factors from moles to moles of different substances, which is chemical equation. We brought in conversion factors for moles to liters for a solution. Right? Are there other phases that we could look at? Like solids? Oh, we have grams to liters or grams to milliliters. Okay, densities. Okay. Could we work with another phase? Like, say, gases? Are gases going to generate more conversion factors? Yes. All we're doing is saying, here's more conversion factors. Use the same process. Nothing changes. All you have to do is memorize one conversion factor. Right? So your total conversion factors for this next test, I think, are 3. Right? But recognizing where to find those conversion factors is the hard part that you need to be practicing instead of practicing the process. Okay? So where to find them, we've got a bunch of lists of things. It is in the slides. It'll show up again later. Okay? But I want to get into our gases, which brings up our next fun phase. Okay? Our gases are now a new phase. We're going to get slightly new rules coming out of them. Okay? Old stuff, variable shape, variable volume, expand and compress, low densities, mix uniformly. All of that was straightforward our very first unit when we talked about matter. The next one that's a little bit weird, gases exert a force on the container that holds them. Is that really true? Do gases exert a force? What happens if we removed all of the gas in this room? Okay, we die, suffocate, let's say we don't need to breathe. Okay, it's a vacuum, so what are you suggesting?
Anti-gravity.
Okay, what's going to happen to our bodies? No. Okay, we no longer have that external pressure holding us. Okay, which means what happens? Our bodies were built to deal with that external pressure. No external pressure, our bodies don't function appropriately. We can get gases coming out of our solutions or out of our bodies. Okay? As the gases try to come out, what do they have to go through? Your skin. Okay? So we could see potential explosions. We could see potential implosions because our lungs are giant air sacs holding air in. Because of the pressure of the air, they stay inflated. If we remove all the air, what do our lungs then do? They're going to collapse inwards. Okay? So we'd see a lot of varying things happen if we change the pressure. So pressure is something that is important, and we can feel that to smaller extents. Say if we drove up to Flagstaff. What happens as you drive up to Flagstaff? Air gets thinner.
Elevation.
Okay? What's happening with that elevation change? Sometimes people recognize it on the way back down. Your ears pop. Why? Your ear is just a skin flap on a drum in your ear, or your ear. Whatever, something like that. There's a skin flap. Okay? That skin flap has air pushing against it. Depending on how much force air hits it, our ear responds differently and we hear things differently. Okay? As we change altitude, we change pressure. Which means when we go up, there's less air, there's less pressure. What happens to our eardrum? Well, it pushes outwards. What happens when we go down? We increase the pressure, and now the eardrum has to pop inwards. And so we can get our ears popping as the drum moves back and forth depending on the external pressure. Okay? Which can be insanely painful if our eardrum can't actually equilibrate. Okay? This, I apologize, is kind of a random spot. Why units? Okay? A lot of people will talk about, well, I just memorize to get moles. I take mass and I divide by molar mass. Okay? But then to get mass, I take moles times molar mass. You memorize 2 equations. Okay? Then you also had to memorize where to find molar mass. If we do dimensional analysis, what do you need to memorize? Where to find molar mass. Okay? And the dimensional analysis method. So that's 2 things versus 3 things. Okay? Mass and molar mass and moles and all that, does that show anything about volume? No. So in the standard method, what do I also have to memorize? I also have to memorize the equations that show volume related back to those. Okay? And atoms. Okay? And molecules. Whereas with dimensional analysis, where do I find the information? I already have one method. That one method allows me to do all of them. Dimensional analysis simplifies the amount of stuff you have to memorize. For those of you who think you have a great memory, memorize the crap out of all the equations. Go for it. Okay? As long as you show your unit work, I'm fine with it. Okay? You will find 2 things potentially happen. 1, you fail in this class because you can't memorize it all. Or 2, you then forget all the content, which is sort of okay. You're accepting that you decided to sit through a class and get nothing out of it. That is your choice. Right? The other option is you have to take more classes in chemistry, which are all going to require you to do more dimensional analysis with more conversion factors. Your list is now going to increase. Okay? So not only will you have to memorize all of these, but another 14 others. If you try to just memorize those facts, you will fail. It's the question of when you fail. Right? Trying to set you up with the tools so that you don't fail, or at least you don't fail catastrophically. You fail minimally in the practice so that you don't worry about it on the exams. Okay? So, when we look at gases, we will look at ideal gas behavior. Why do we pick ideal systems as opposed to real systems? Do real humans kill each other? Yeah. Do I want to live my life based on real humans then? Because real humans kill each other. Should I be in this room if you are a human and real humans kill people? Why am I not going to want to be in this room? You're going to kill me. That's not really fun. I think I'm going to avoid you. By that same token, you're all like, ha, I could kill you. Look around. You're in the same room. I could just as easily kill you. Okay? That's not cool. We base our lives around ideal systems, what we expect people to ideally do. Okay? Why? It makes life easier. We do the same thing with chemistry. We look at ideal gas behavior because ideal gases are easier to model and manipulate. If I looked at a real gas, it gets crazy difficult to manipulate. So I try to come up with an ideal system that allows me to understand and come up with simple approximations that are mostly correct. Okay? Some of those big assumptions. Gases are made up of super tiny molecules. Well, we knew molecules were tiny. We're actually, with gases, taking it a step further. Our gas particles are so tiny, they don't have a volume. Okay? If we were a gas particle, the first person in here could sit where? Anywhere. Where can the second person sit? Anywhere where the first person isn't. Does that mean your volume for the room has changed? Yeah. With gases, we don't want to have to worry about how many particles are there because as we add more particles, what happens to the volume? It would change. I don't want to worry about that change, so I say gas particles don't have volume. Now I don't have to worry about that. The volume of the container is the volume of the container regardless of how many gas particles are there. That simplifies calculations. Okay? The next one, gases move in rapid random motions, straight lines. We don't get any kind of weird curves, okay, or weird spins, because those weird spins and curves could make life more difficult. Okay? When you first learn pool, people have learned pool, or at least know what it is. Like 2 people, okay, awesome, 3 people.
Like billiards?
Yes, like billiards. You're right. I apologize.
I thought it might clear it up for people.
Yeah, billiards.
Clearly not.
Okay. If we go through and play billiards, do you start by trying to get the ball to jump over other balls? No. When does that happen? When you're pretty good at it. Or like if your parents are pool sharks and they're teaching you awesome things. Okay? Most people don't learn how to get balls to jump over other balls, right? Okay? Because that's tricky. That's hard to mirror, that's hard to manage. So when we look at gas molecules, we do the same thing. They only move in straight lines, okay? And they're relatively rapid, okay? And random. The next one, gas particles have no attraction for one another, okay? This becomes really, really important, okay? Kind of ties back to the random directions. If there's an attraction for one another, what happens? They aren't going to be random, which then means things start to move in certain directions or pool around certain areas. We get a non-uniformity of the gas, which makes it more difficult to predict and model. Okay? So we want to make sure that we keep attraction out of it. Right? They collide without losing energy, similar to billiards. And the last one, the kinetic energy of a gas increases proportionally to the temperature, meaning the more motion there is, the more heat there is within it. Or if I increase the heat, the more motion. Yes?
Is that supposed to be the lowercase delta? Is that what that's supposed to look like?
No.
Or is that something different?
This right here is actually known as a proportionality. Probably not.
Okay, it looks
Okay.
really similar to the other one.
Sort of. The delta is this way. The proportionality is this way, sideways. Okay? So those are kind of our big ideal gas behaviors. Because it's an ideal gas, we can get an extra conversion factor that Molly threw out there that showed up in chapter 8 that I told you not to read about, but you may have read about anyway. 1 mole of any gas is equal to 22.4 liters. Okay? Moles related to liters. Didn't we just talk about moles related to liters? What did we call it? Molarity. When was molarity true? For? I'm positive you said it, but maybe you didn't. A solution. What is this true? For gases, and in particular ideal gases. So this is a valid conversion factor. It allows us to relate these two things, moles and liters, but it only works for gases. Okay? I have a big problem with it showing up in chapter 8. First reason for it. Okay? They addressed this mole to liter conversion for gases in chapter 8. Have they talked about solutions yet? No. Did they talk about molarity? No. So they're bringing in gases before solutions. Well, that must mean because gases are more frequently used. How many reactions have we done this semester in the gas phase? 0. Why not? When you produce a gas, where does it go? Into the air. And where's the air? All around us, which means you do a gas phase reaction, where does that product go? Into your lungs. That's dangerous. That's stupid. We don't do it. Okay? So gases don't make any sense to talk about early on because you're probably not going to work with them. You're probably going to work with solutions, not gases. Okay? The next big reason behind it, okay, or the next big issue, is will you ever work with gases? Again, for the safety hazard, probably not. Okay? So it's not super likely that you will ever need to use an equation like this. Okay? The next big fun thing with this one, which makes me extra irritated, and we'll get there in just a second because Nick has a question.
Well, so you won't even do anything like that in YoChem or in like...
Nope. No. Yeah. There's the rare case that maybe somebody tries to bring in gases. And unfortunately, typically when those gases are being brought in, this equation won't be valid because it won't be an ideal gas. Okay? The last thing, we've seen parentheticals before, and usually what are those parentheticals in reference to? Exceptions. Okay? This statement is true. So we see an equality, and what do you think? If I say 1 equals 1, what do you think about 1 equals 1? When is 1 equals 1? All the time, always. So when I say 1 mole of any gas equals 22.4 liters, you go, that is true? Always. Well, number 1, no, it's a gas. Okay? It doesn't work for any other thing. Number 2, exception. So immediately it's a dumb thing to make you memorize because there's exceptions. Maybe those exceptions aren't that big a deal. What is STP? Standard temperature and pressure. Okay? Pressure isn't all that bad. Okay? Pressure we keep at 1 atmosphere, and while elevations change pressures, it doesn't change it hugely drastically.